Okay, so we'll start the class now. We are discussing about some problems on how we can design a helical spring when it is subjected to a given tensile load or compressor load. So today we'll take up one more problem in that way. And first you note down this problem, then we'll discuss the solution. So take a 2 minutes time to note it down, then we'll discuss the solution. Now we note it down. Okay, is it over? 354 నోట్ చేయడం అయిపోయిందా? ఎవరు రెస్పాండ్ అవ్వరంటారా? క్లాస్లో ఉండరా లేరా?
సార్ అవ్వలేదు సార్.
రెస్పాండ్ అవ్వరా? అయిందా లేదా అంటే అవ్వలేదు సార్ అని చెప్పాలి కదా. ఓకే, నోట్ ఇట్ డౌన్.
Yes, sir.
Okay, right. So now we'll see the solution. First, I'll read the problem and then I explain what is the given data, and then we see the solution. A railway wagon moving at a velocity of 1.5 meters per second is brought to rest by a bumper consisting of two helical springs arranged in parallel. The mass of the wagon is 1500 kg. The springs are compressed by 150 mm in bringing the wagon to the rest. A spring index can be taken as 6. The springs are made of oil hardened and tempered steel wire with ultimate tensile strength of 1250 Newton per mm square. The modulus of rigidity of 81370 Newton per mm square. The permissible shear stress for the spring wire can be taken as 50% of the ultimate tensile strength. Design the spring and calculate 1 wire diameter, 2 mean coil diameter, 3 number of active coils, 4 total number of coils, 5 solid length, 6 free length, 7 pitch of the coil, and 8 required spring rate and 9 actual spring rate. Okay, so this is the problem. So this problem is also similar to the previous problems, but only difference here is, so while designing the spring itself, I already told that the two required parameters to design any helical spring is load and deflection. In the first problem, if you see the first problem, both are given directly. In the second problem, load is given in the range and deflection is also given in the range. So that means delta is given indirectly. Now coming to the third problem, of course it is an helical tension spring, so which is similar only. In that problem also delta is given indirectly. So we identify that and we solve in the same manner. In this problem also, he has given the delta directly. Now deflection in the spring is 150 mm he has given. So the springs are compressed by yes. So in this, as given, the springs are compressed by 150 mm. So that means this is delta is given, but load is not given here. Load is P. You required P and delta. So to design helical spring, you required P and delta. Delta is given. So in the first problem, both are given directly. In the second and third problem, this delta is given indirectly. We identify the delta. In this problem, he has given load is indirectly and delta is given directly. So remaining parameters are same. Spring index is given, allowable shear strength is given, and G is given. Everything is given. So and also you need to calculate the same parameters only. So everything is same. Only thing is in this problem the load is P is given indirectly. So how we can compute that P here? So for that he has mentioned where the springs are used. So here the springs are used in a buffer. So I have two springs arranged in parallel, means the parallel arrangement I'll show something like this. So this is a buffer. Then I have a wagon, whatever it may be, railway wagon. Okay, he said it is railway wagon. So which is having some mass here, and it is moving with a velocity v, and it come and hit this wall. So then, if the wagon is coming with some velocity, so therefore it has some kinetic energy. So it has a kinetic energy because the mass is moving with a velocity, which is given by half mv square. The formula for our half mv square, kinetic energy is half mv square. So mass is given to you 150 kgs, and velocity is also given 1.5 meters per second, meter per second. So you can compute the kinetic energy. So now, while moving with this velocity, it hit this bumper and it stated that this wagon is come to rest. That means what happened to this kinetic energy? Rest means velocity will become zero. After hitting that, its velocity is zero. So that means kinetic energy becomes zero. So that means what happened to that? As per our law of conservation of energy, energy will be transformed from one form to the other form. That means whatever may be the kinetic energy of this wagon, that kinetic energy is taken by these springs in the form of a strain energy. So while hitting this, then what happened to the springs? The springs are compressing. That's what you have already stated in the problem also. The springs are compressed. So while compressing, while the springs are compressed, they store some energy. That energy we'll call it as a strain energy. That strain energy, where it comes from? That comes from this kinetic energy of this vehicle. So that means since the kinetic energy is zero, then this entire kinetic energy is converted into the strain energy. So how I can calculate the strain energy formula? What is the formula for strain energy? Strain energy is equal to half into P into delta, where P is the load on the spring and delta is the compression or elongation of the spring. But here, how many springs you have? Two springs are there, two helical springs are there, and they are in parallel. So therefore, I need to take the strain energy of the two springs is one spring, it is half P delta. Since they are in parallel, I have to take 2 times half into P into delta. So then this should be equal to your half mv square. So in this, right side is completely known to us. M is given, V is given. Left side, delta is given, only unknown is P. So therefore, I can calculate P. Once I have P and delta, then the remaining procedure of designing the helical spring is same. You need to use stress equation to find out the Y diameter and mean coil diameters, delta equation to find out number of active coils. Once you have done that, then you need to assume some style end, some type of ends for the style ends. Then from that you can identify what are the number of inactive coils. Once you have done that, then remaining things, solid length, free length, pitch of coils, all these things you can easily calculate it using those parameters. Finally, required spring rate and actual spring rate also you can calculate. This required spring rate is nothing but this P by delta, what you have to do. Actual spring rate is, you need to use the formula for the delta of the spring. Using that, you can find out this actual spring rate also. So now, we'll see all those steps one by one. So first, this is the given data, what he has given in the problem. Mass of the wagon is 1500 kgs and it is moving with a velocity v is equal to 1.5 meter per second, and delta compression of the springs is 150 mm and spring index is given as 6, SUD is given as 1250 Newton per mm square, then G is given as 81370 Newton per mm square, and also has given that the allowable shear stress is 50% of the ultimate yield strength. So this is 1250. So now first what we need to do is, because the load is unknown here, you know the delta, P is given indirectly. First you need to estimate what is this P. For that you need to use law of conservation of energy. So that means the energy stored in the springs should be equal to the kinetic energy of the wagon. So already tell you that equation. So the kinetic energy of the moving wagon is absorbed by the springs. So the kinetic energy is given by half mv square, like already told. If I substitute that data half into m into v square 1.5 square, it comes out as 1687.5. But here the unit is, this is important, units are in Newton meter because I have taken velocity in meter per second. So here I'll get only Newton meters. But our delta is given in mm. So you can see that here delta is 150, which is given in mm. So you need to convert this one is also into this meters also into mm. So if I do that, what I need to do is 1687.5. So if I convert meter into mm, it should be multiplied by 10 power 3 into 10 power 3 Newton mm. This will become 1687.5 into 10 power 3 Newton mm. So this is the kinetic energy. Then we need to equate this kinetic energy to the strain energy of the springs. Suppose P is the maximum force acting on each spring and causing it compressed by 150 mm. The strain energy absorbed by the two springs is given by, like already told, strain energy S is equal to 2 into half into P into delta, 2 into half into P into delta, which is, if you calculate this, it comes out as 150 P Newton mm. So here it is in Newton mm. That's why here we converted this one is also into Newton mm. Now equate these two so that you get the P value. The strain energy absorbed by the two springs is equal to the kinetic energy of the wagon. So therefore 150 P is equal to 1687.5 into 10 cube. So then if you simplify this, from this we get P is equal to 11,250 newtons. So therefore now we have P and then we have delta and of course we have C also. Now use the deflection equations and stress equations to determine the parameters of the spring. So I'll take P as 11,250 newtons and first we'll calculate what is the wire diameter. So for that, first we will compute what is the allowable shear stress, that is the permissible shear stress is given by 0.5 times SUT, which comes out as 625 Newton per mm square. Then since C is already given, you need to calculate what is the wall stress factor. So for C is equal to 6, it is 1.2525 only. Then your resultant shear stress stuff is K into 8 Tc by pi d square. So which is equal to 540. Maybe here it is wrong. It is not 545. It is 625. The allowable shear stress here it is 625. You need to substitute 625 here is equal to 1.2525 into 8 into 11,250 into C by pi d square. So if you simplify that, you will get D is equal to 18.56 mm, or which may be rounded up to 20 mm. So we identify the first parameter, that is wire diameter. So once you have wire diameter, then you can find out the capital D. Mean coil diameter is nothing but, if you multiply this D by C, you will get that. Or the same thing here. So mean coil diameter CD is nothing but, C is given as 6. We computed this diameter of wire as 20. So your mean coil diameter is going to be 120 mm. So these are the first two parameters we can get from this stress equation. Then you use the deflection equation to find out what are the number of active coils. So therefore third step is you need to identify what are the number of active coils. For that you need to use delta formula. So delta is equal to, this is the formula, 8 PD cube n by gt power 4. Delta given as 150. So P is we calculated as 11,250 newtons. And D we computed as 120 mm just now. We get 120, yes, 120 only. See here we got it at 120. Then N we need to calculate N. So G is given as 81370 and small d is 20. So if you substitute all these things and if you simplify this, we get N is equal to 12.56, which is rounded up to 13 coils. So number of active coils is 13. Then you need to identify the style of the ends. Then from that you identify what are number of active coils. Total number of coils is nothing but your number of active coils plus inactive coils. So here the ends are assumed as square and ground ends. So therefore there are two number of inactive coils are there. Therefore your total number of coils is this 2 plus this 13, which is going to be 15. So total number of coils will become 15. So that's it. So that is about this total number of coils. Then you need to find out what is the solid length, what is free length, and then what is the pitch of the coil. So to find the free length of the spring, you should know what is solid length and what is delta and what is total gap between the coils. Total gap. You need to determine these three parameters. So sometimes this total gap can be taken as 0.15 times delta. 0.15 times delta, or else sometimes they may assume the gap as some 0.5. The range is 0.5 to 2 mm. So you can assume any value in between these two values, 0.5 to 2 mm. So based on that, so this is the gap between adjacent coils of one set. So number of coils minus 1, you'll get the total number of those pairs. So you multiply that one with this, you'll get the total gap. So in this problem, since he has not mentioned this one, we'll assume the gap. So before that, first we need to compute what is this delta. Delta is, again the formula is same this, but only thing is we need to substitute for the n, which is nothing but 13, so that you will get the actual deflection. So this deflection he has given 150, but the actual deflection we are getting it as, with these parameters we are getting it as 155.29 by substituting all this data. Then solid length is nothing but the number of coils, total number of coils into d, which comes out as 300 mm, and he has assumed a gap of 2 mm. So therefore our total gap is nothing but 15. So total number of coils 15 minus 1 into 2, which comes out as 28 mm. So then your free length is going to be the solid length plus total axial gap plus delta. If you compute that, you will get it as 483.29, which is rounded up to 485 mm. Once you got the free length, then pitch of the coil is nothing but free length divided by number of coils minus 1. So pitch is given by free length divided by total number of coils minus 1. So 485 divided by 15 minus 1, which comes out as 34.64. So now once you have done all these things, then the next step what you asked is, what is the actual spring rate, or what is the required spring rate and what is the actual spring rate. So actual spring rate you will get from the delta formula. So that means whatever delta we computed here, actual deflection. So this actual deflection will give you, this is 155, but whatever delta he has given, this is the requirement. So if you use this delta, you will get the required spring rate. If you use this delta, you will get what is the actual spring rate. So that is the two formulas you need to use. So required spring rate is nothing but P is 11,250 by given value delta 150. So it is comes out as 75 Newton per mm only. If you want to convert this one into meters, then it is going to be 75 into 10 cube Newton per mm. So then if you want to compute the actual spring rate, so in case of this, you have to substitute what is the actual spring deflection. So actual deflection we got it as, already we calculated here, that is 150, yes, somewhere here, yes, 155.29. You can substitute directly that one. P is 11,250 divided by that 150.29. So you'll get the same 72.44. Or else you can use this formula also. Either way you are going to get the same value. So here this should be equal to your load P by delta. 11,250 divided by, what is the delta value? Delta value is 155.29. So if you substitute 155.29, you should get the same value, which is 72.44, even with this formula also. Or if you use this formula also, you should get the same value. Right? So this is how you can solve this particular problem. Okay? So I think with this, we covered all types of problems on the springs. We covered all types of problems. So I'll close this one, design of helical springs when they are subjected to static loading. How we can design these springs. So then we'll move on to next thing, that is fatigue loading. Design of springs under fatigue loading. Before going into that, if you have any doubt in this particular problem, or maybe in the previous problems, whatever we discussed, you can ask your doubts. So if once your doubts are clear, then we'll move on to the next one. Anybody is having any doubt in this particular problem, or maybe the problems what we discussed in the earlier classes also? So because we are running out of time, we need to go fast because we have one more topic after this. We need to discuss about helical leaf springs also. That is also part of the syllabus. So we need to complete that also. So anyway, so we'll discuss all those things, no issue. But if you have any doubt now, then you can ask it. Everything is clear? If you say yes, I'll move to the next topic. Okay. Nobody is responding. I don't know whether you understand it or not. Anyway. So,
sir, we understood, sir.
Huh?
We understood, sir. No doubt, sir.
Okay, right. Very good. Then we'll move on to the next topic, that is design against the fluctuating load or fatigue load. Fluctuating load, or we'll call it as a fatigue load also. How we can design the springs. So in this, we are not going to design the spring actually. What we'll do is, just we'll try to determine what is the factor of safety when the load is fluctuating within the given range. That we'll calculate. So once you have a factor of safety, then the remaining design is going to be based on the static procedure only. So what we do is, we'll pick some wire diameter, small d. So then with the diameter, you need to verify that whether your factor of safety is more than 1 or not. So if factor of safety is static, that is static factor of safety, not for the static load factor of safety, you need to determine. So once you are satisfied with that, then the remaining design is going to be based on the static load procedure only. Only the diameter will choose frame based on the fluctuating load. Okay, right. So now coming to this design against fluctuating load or fatigue load. So what we need to discuss, like I already mentioned, we'll concentrate on how we can determine the factor of safety. So to determine the factor of safety, what is your equation for that? So how we can derive that equation? So for that, you need to recall your SN diagrams. Not only SN diagrams, what you have to do recall is, so Soderberg line or Goodman's line. So we use the, in case of fatigue failures, we discuss these kind of failure equations. Soderberg line, Goodman's line, and Gerber's parabola, all these things. So the same concepts we'll use here only, but here we'll apply those concepts to the spring application. That is the only difference here. Okay, right. So in many applications, the force acting on the spring is not constant, but varies in magnitude with time. So why it is? So if you remember in the problems what we discussed earlier also. So we discussed these applications of the springs also. What are the applications generally? So now I think in problem number 2, we use the spring as a wall to operate the valve. So in case of valve, when valve is open, there is one spring, one force on the spring. When valve is closed, the force is changing. That means always the force is not constant. It is going to change with respect to time. That means it will vary its magnitude. So of course its direction is remain same, but only thing is the magnitude is going to vary with respect to time. That is one application, one kind of application. What we already discussed in that numerical problem is valve. So in order to control the valve, we use the spring. So I think if you remembered it, I'll go back to that problem also. I'll show it to you. This is helical spring. This is okay, tension spring. Yes, this one here. So in this particular problem, we discussed that. So and also as see, you can see that the load is varying 300 Newton to 150 Newton. So now, if I bring this application and if I say the spring is subjected to fluctuating load is changing 300 to 150 Newtons here. See this closed position and it is the open position. In the open position, the load is 150. In closed position, the load is in open position load is 300 Newtons. In closed position, it is 150 Newtons. So load is changing. But you may have a doubt here. So we already discussed this problem. We already solved this one and solution is also over. But we are not, even though the load is changing 300 to 150 newtons, we are not discussed about anything about the fluctuating load. Actually, the load is varying means you need to design for the fluctuating load. But we ignore that and simply we design for this maximum load 300 newtons only. So that's what I already told in the at the beginning of this topic, that is design against fluctuating loads. So the design is basically only based on the static load only wire diameter is calculated for fluctuating load. So here, since we are designing for the 300 newtons, so I can use the static design procedure only or design procedure for the static loading only. But only thing is, after designing the spring, I need to check for whether, because of this fluctuating load, the factor of safety is more than 1 or not. I need to verify that. Or the spring can withstand this fluctuating load or not. So that's why, even though the load is fluctuating, we'll design the spring for only the static load by taking maximum load. So now if you want to consider the fluctuating nature of the load, what you have to do is, you need to determine what is the factor of safety when the load is fluctuating from maximum load to the minimum load. So that means, even in the examination also, don't confuse when if he has given the load is changing from one value to the other value, like in this particular problem. Load is changing from 300 newton to 150 newtons. Don't think that the load is changing from 300 to 150, then you need to design based on the fatigue equations or fluctuating load equations. You need to use the static design procedure only, as long as if he doesn't mention anything in the problem. So then suppose I'll show you the problem also, how they can give, if you want to use fatigue equations, how they can frame the question, or how you will get a question in the examination point of view. That we'll see also while discussing about those problems. So for time being, what you need to remember is, even though the load is changing 300 to 150 newtons, you need to design for the static loading only. So that's what we did in this problem. We already discussed this problem. We designed the spring for the static loading only here. Okay. Even the load is changing from 300 to 150. Even the load is fluctuating load also. Simply if he asks you design the spring, then you have to use static loading only. Static loading is static design procedure only. Anyway, so coming to that particular slide. Yes. Okay, so why I have taken back that one is, so this is the main reason why the magnitude of the force is varying is because you are using the spring in such applications. Or else if I take application in automobiles where the springs are used in a suspension system, there also the load is not constant. So depending upon the road bump, the magnitude of force will change. So there also it is there. Okay, and of course he has given these applications also here. The wall spring of an automobile engine is subjected to millions of stress cycles during its lifetime. So therefore it is a fatigue load. It is subjected to a fatigue load. On the other hand, the springs in linkages and mechanisms are subjected to comparatively less number of stress cycles. So here, more number of life cycles means, suppose if you are using a spring for application which is used to operate a valve, so then it is subjected to millions of stress cycles, means you need to design this spring for the infinite life, because your number of stress cycles are in millions here. So you need to design the spring in terms of for infinite life. Whereas on the other hand, if we are using the same spring in the application like a linkages and mechanisms, where it is subjected to a relatively less number of stress cycles. So here you need to design the spring for finite life. So therefore, the springs which are subjected to fluctuating stresses are designed on the basis of the two criteria, that is design for infinite life or design for finite life. That depends upon the application where you are using the spring. If it is using in case of wall applications, you need to design the spring for infinite life. If it is used in the application like where it is subjected to less number of stress cycles, you need to design it for finite life. So then we will see what are the equations we need to use to design the spring for either finite life or infinite life. So let us consider a spring subjected to an external fluctuating load which changes its magnitude from P max to P minimum. So that's what, since if you say it is the load is fluctuating means it is varying. So because it is varying, definitely it should have a minimum value as well as a maximum value. So let denote those two loads as highest value is going to be P max and lowest value is going to be P minimum. So therefore, if you have P max and P minimum, from that you can calculate mean force as well as force amplitude or amplitude force. This is nothing but PM denoted by PM and PA. Mean force is nothing but average of these two, that is P max plus P minimum by 2, and amplitude force is nothing but P max minus P minimum by 2. So this we already know these things. So while discussing about fatigue analysis, there in the second unit we discussed all those things. So how we can calculate amplitude of a load and mean of a load. Mean is nothing but P max plus P minimum by 2, and the amplitude is P max minus P minimum by 2. So once I have P mean and P amplitude, then I have a resultant stress equation, resultant shear stress equation. That's what we discussed in case of the design of the helical spring. So we'll use those equations to determine what is mean shear stress and what is amplitude shear stress. So then I can apply the Fatigue-Soderberg equation or Goodman's equation to determine the factor of safety in the design. So therefore, the mean stress is calculated from the mean force by using shear correction factor Ks. So here this is important point. We already discussed this one while discussing about this Ks and Kc and K. So here what you have to do is you need to apply the correction factor for the mean stress only. You have to apply Ks, that is the correction due to direct shear stress only. So that means while calculating this mean stress, you need to use only Ks. So therefore, your mean stress tau m is equal to Ks into 8 into, you have to consider the mean force or mean load Pm into d by pi d cube. Using this formula, we can compute what is the mean stress. Similarly, the amplitude stress, whereas this Ks is given by this formula. Ks is the shear stress correction factor due to only direct stress, 1 plus 0.5 by C, or this one plus 0.5 d by capital D. Then you need, once you calculate the mean stress, then you need to calculate amplitude stress also. Ks is the correction factor for the direct shear stress and it is applicable to only mean stress. So you have to apply Ks only for mean stress. Then the torsional stress amplitude, tau A is necessary. It is necessary also consider the effect of stress concentration due to curvature also in addition to the direct shear stress. Therefore, you need to take your tau A expression is Ks into Kc into 8 Pa d by pi d cube. So here important point is while calculating the mean shear stress, you have to use mean load and you need to apply Ks only. So this you need to remember. Of course, maybe these formulas are available in data book also. You can refer the data book. In the data book, these formulas are available. Then, while calculating the tau A value, you have to use Pa and then you have to use K. This is wall stress correction factor. You need to use K value. So then, once you have tau M and tau A, then you can construct your failure equation for the spring under fluctuating load. So there is a basic difference between the rotating beam specimen and fatigue testing of spring wires. Why it is different? So if you recall it, we already constructed, this is going to be our Soderberg line and this is going to be the Goodman line and this is going to be a Gerber line. You get something like this. If you plot a mean stress, here it is mean stress, and here it is going to be the amplitude stress. So here it is SYS and this is SYT, something like this. So using that, you already discussed this failure theories. But so these theories, what we get it is we calculated or we derived these equations based on the fatigue strength what you are getting from the rotating beam specimen. But I cannot use directly those values here. Why? Because there is a difference between the rotating beam specimen experiment and the springs which are subjected to this actual load. So in case of rotating beam specimen, what type of load you are using? In case of a rotating beam specimen, you are using a completely reversible stress. That means one side it is maximum negative value, another side it is maximum positive value. So then we'll call it as a completely reversible load. Whereas that is your rotating beam specimen is subjected to. Whereas the springs are subjected to either compression load or either tension load, not both here. So your rotating beam specimen is subjected to both compressive stress as well as tensile stress simultaneously, whereas the springs may be subjected to either tensile load or compressive load only. Why? If I take helical compression spring, it can take only compressive load. If I take helical tension spring, it will take only the tensile load. So therefore, I cannot use whatever the criteria which I follow for this rotating beam specimen. That means these equations are not valid in this case. So we need to further modify these values. So to modify that, again we look at into the experimental data available in the literature. So that's what is stated here in this statement also. A spring is never subjected to a completely reversible load, changing its magnitude from tension to compression and passing through zero with respect to time. So that means your rotating beam specimen is subjected to a completely reversible load where it is subjected to tension stress as well as compressive stress, which is passing through zero value also. Whereas your springs are subjected to either a helical compression spring is subjected to purely compressive forces. Like already told, helical compression spring is subjected to only compressive force, whereas helical tension spring or extension spring is subjected to purely tensile force. That means you don't have two types of stresses in case of these springs, helical springs. So that's why here your equations are different for the spring when compared to the equations of this rotating beam specimen. So if you see that how the load is also varying in case of this helical springs. So at max the load is going to be zero only, then it will go to the maximum value. So it won't go to the other side. So if I take the load is a positive value, then always the load is on one side of your zero line. It won't go beyond this point. You're going to have a cycle something like this, stress cycle something like this. So therefore, either if it is a compression spring, so it is on the one side. If it is a tension spring, the load is the other side. So that means always the load is one side of the zero value. So it may be positive force or it may be the negative force, but not both positive as well as negative. So in general, the spring wires are subjected to pulsating shear stresses. So then we already discussed this kind of load also, we'll call it as a pulsating load. So that means when a load is changing between 0 to maximum value. So that means if the load is changing from negative value to positive value, then we'll call it as a reversible load. We'll call it as a reversible load when it is changing negative to positive. In between, of course, it has to pass through zero value also. So then we'll call it as a reversible load. Whereas if it is changing negative minimum value to negative to zero or 0 to maximum positive value, if this kind of case, then we call it as a fluctuating load or a pulsating load. So these springs are subjected to either this kind of load or this kind of load. If it is a helical compression spring, we may have a situation of this kind of thing. So the load is compressive, maximum compressive force to zero. Whereas when if you are using a helical tension spring, it maybe comes under this category. That is, the load is changing from 0 to a maximum positive force. So therefore, whether you are using a tension spring or a compression spring, they are subjected to only fluctuating stresses. That's why we call it as the springs are subjected to fluctuating stresses, which vary from 0 to the maximum value. The maximum allowable here it is SC dash. That is nothing but, see, in case of rotating beam specimen, we have seen that SC dash, that is nothing but the endurance strength of that material. So here also endurance strength or endurance limit. Here also this is SC dash is nothing but the endurance strength in shear of the spring material. Why you use a dash means, so if you recall it correctly, first we determine the SC for a material and then we apply some correction factors to this SC so that you got SC dash. Those correction factors are Ka, Kb, Kc, Kd, something like this. So load factor, size factor, correction, temperature factor, all these things we applied to this SC, we got SC dash. Similarly, here also you need to apply some correction factors based on the given environment. That's why you are getting SSE dash. So, which is nothing but the maximum allowable shear stress in the spring when it is subjected to a fluctuating load. So, therefore, this SSE dash is called the endurance limit in shear for the stress variation from 0 to maximum value. So, now that means the design criteria is if the shear stress is less than this endurance limit in shear, then your design is safe. Otherwise, you need to modify your design, or your design is going to fail under the given loading condition. So therefore, how we can estimate this SE dash? That is the next question. How you can estimate this SE dash? Again, you need to go for the experimentation to find out these values. So, but there is so far a small amount of information is available in the literature. So we'll use those properties, and instead of going for the calculations, straight away we'll pick the data from the data book and we'll use those properties. So the data regarding the experimental values of endurance strength of a spring bias is not readily available. So because for all kind of spring materials, so this experimental data is not available, and also there is no theoretical computations also available. So in the absence of such data, what we'll do is we'll use these are the properties for the springs. So if I use patent and cold drawn steel wires for the spring material, I have to take SC dash as 0.21 times SUD, and SY is the yield strength in shear. I'll take it as 0.42 times SUT. Or else instead of patent and cold drawn steel wires, if oil hardened and tempered steel is used as a wire for the spring, then you have to use these are the relations for your SC dash, SSC dash, and SY. So SSC dash is nothing but 0.22 times SUD, SSY is 0.45 times SUT. So now if I know this, then I can use these equations in the failure criteria. So for that, I need to construct what is that failure equation or failure line, where SUT is the ultimate temperature. This SUT you will get it from the data book. SUT for this materials you will get the data from the data book. You will get it these values, or maybe in the problem data itself. Sometimes they may give this SUT value. Okay, right. So now this is the diagram which illustrates the failure line for the spring which is subjected to pulsating stress. So for that, we need to take on abscissa, you need to take the mean stress value. So you can see that here, this is the axis. On this axis, horizontal axis, you need to take mean stress, which we call it as abscissa as the mean stress, and the vertical axis nothing but ordinate. On the ordinate, you need to take it as a tau A. So then, if you plot the failure curve, then you will get the design line or design equation for this springs which are subjected to fluctuating stress. The mean stress is plotted on the abscissa, while the stress amplitude on the ordinate. Then the point A, see now here, it is a straight line only. For simplicity, it is taken as a straight line only. So here, this is the point A and point B are the your failure points. If your design point lies above this point, then you can say that spring is failed. So even though your experimental data is going to be a curve, some kind of thing, we'll estimate it as a straight line, which is a line of failure here. But for this line of failure, still we'll apply some factor of safety here. So if I apply a factor of safety here, therefore this is going to be the design line. So this is the failure line and this is the design line. Now we need to see what are the coordinates of these points. So extreme points of this design line and failure line. So these A and B are the points of your failure lines, and C and D are the points of your design line. So now I need to see what are the coordinates for this A and B. So for A, so this is going to be your SE dash, SE dash by 2, even this is also SE dash by 2. So then for this, if you divide that SE dash by 2 by factor of safety, you will get the points for the C and D also. So that's what you have written here. Point A with coordinates SSC dash by 2, SSC dash by 2. So that means these are the coordinates for point A. Indicate the failure point of the spring wire in fading state. Test while subjecting to pulsating stress cycle. Then point B is on abscissa. On this point, indicates failure under static load condition when mean stress reaches the torsional yield strength. So you can see that here it is SY. So therefore line AB is called the failure line. Similarly, you have a design line, so which is having endpoints as C and D. So the consider the effect of factor of safety. So like already said, this is the factor of safety. This much is the factor of safety we are applying factor. To consider the effect of factor of safety, a line DC is constructed from the point D on the abscissa in such way that your OD, so from point O to point D. So this is nothing but your SYS by EFS. So now I have a point D. Similarly, I need to identify point C also. That point C is nothing but this SAC dash by 2 divided by factor of safety. I'll get this point. Then if I join those two points C and D, I'll get the design line. Once I have a design line, now if I want to use Goodman's criteria, I need to construct what is the load line. So load line is nothing but this one. So here you will get the load line is based on the ratio of your mean load or tau A by tau M. So which is nothing but tan theta here. So the load line makes an angle theta here. You can see this theta. This theta will get is the ratio of amplitude stress to the mean stress. So now if I draw a line based on that, then I'll get a load line. So now this load line and this CD intersection of this point is going to get the design point or failure point for our problem. So that's what he said. Line CD is called the design line because it is used to find the permissible stresses with a particular factor of safety. Line GH is called load line. So this line is GH is the load line. It is drawn from the point G on abscissa at a distance of tau I from origin. So how will you identify this point G? So you need to calculate this tau I. Tau I is nothing but the mean stress value by applying this factor of safety. So once you identify this, then with theta value, that theta is tan theta is equal to tau I by tau M. Using that relation, you can construct this line. The torsion stress due to initial preload on the spring is nothing but your tau I. So you can identify the tau I here because of initial preloading. So once you have tau I and theta value, then you can construct this load line. The line GH is constructed in such a way that its slope theta is given by, just now I told, tan theta is equal to tau A by tau M. So then you can easily construct this load line. So then the pointer of intersection of design line DC and load line GH is X. So this is what I can call it as a design point for this particular application based on the chosen factor of safety. So therefore the coordinates of this point X are going to be tau M and tau A. Considering similar triangles, now to design that failure equation here, so you have to consider the similar triangles. So this is one triangle I can consider, and this is another triangle I can consider. Or instead of those two triangles here, what I need to consider is, because I am interested in this X here, I'll consider this triangle. This is one triangle. So what is this triangle? XFD. That's what he said, XFD. Then AEB. So AEB. This is another triangle. So if I use the properties of similar triangles here, I can write, see here, this is one smaller triangle which is inside this bigger triangle. This is the bigger triangle. So now here, if I use the properties here, so this side divided by this side should be equal to, I can use this side divided by this bigger side. So that's what he written here. XF means this side, XF divided by FD, this one, XF divided by FD, it should be equal to your AE divided by this bigger side, EB. So that's what you will get from your properties of similar triangles. Now if I substitute what is this XF, FD, AE and EB, I'll get the failure line, design line equation. So that is nothing but it comes out as something like this. Your XF is nothing but your amplitude stress. So where here a X point coordinate, just now tau M and tau A, XF means it is a coordinate on ordinate. If I expand to here, I'll get tau A only. So it is tau A. Then FD. So FD is nothing but this distance. FD is this distance. Up to this point, it is tau M. So then in that I need to subtract this tau I. So therefore SYS by FS minus tau m, the coordinate for this or the length of this line FD. Similarly, AE, so this AE is nothing but here, this one half into your SE dash divided by this total line. So this total line nothing but if I take from here to here, in that if I subtract this distance, I'll get that. So from here to here it is SSY, that is SSY. Then I have to subtract this one, this is nothing but again the same thing here, SC dash by 2. So then this is finally I'll get the equation for the design of this helical springs which are subjected to this fluctuating or pulsating loads. So in this equation, if I know all these things, I can calculate the factor of safety. So if I know what is tau A, what is tau m, of course the remaining thing are the material properties. SSC dash and SY, they are material properties. Once I decided the material for the spring, I can take that. So only thing is I have to compute what is tau A and tau m. So based on that, I can calculate what is factor of safety for the design. If the factor of safety is as per the requirement, then you can say the spring design is safe. Otherwise, you need to modify the design so that you get the required factor of safety. So this is how you can design the spring for a fluctuating load. So that means, so in the examination point of view, they may ask you calculate what is the factor of safety based on the fluctuating load. Means you need to use only this formula. So in this formula, you need to get what is tau A, what is tau m. So I already shown you the equations, how you can compute the tau A and tau m. So in the beginning, we have seen those equations. Those are the important things here. Tau A is calculated based on amplitude of the force. I'll go back. Yes. Yes. See, this is the formula you need to use for the tau m. So to calculate tau m, you require Ks and Pm. We know the formula for Ks. Ks is nothing but 1 plus 0.5 by C, and mean load. Pm is the mean load, nothing but maximum load plus minimum load divided by 2. Similarly, tau A is calculated based on K and Pa. So you have to compute K, that is wall stress factor, which is given by 4C minus 1 by 4C minus 4. 4C minus 4 plus 0.615 by C. This is there, already there. So you have to use this one to compute this K, and Pa is nothing but P max minus P min by 2. P max minus P minimum by 2. So therefore I'll get tau A value and tau m value. So then once I have that, then based on the material, so I have chosen here, I can pick the SSC dash and SYS values. If I use patent and cold drawn steel, I have to use these are the formulas, or these are the values. If I use oil hardened and temper steel, I need to use these are the formulas. So then in that equation now everything is known to you. In this equation everything, tau A is known, SSC dash is known, except Fs, everything is known. So now if you analyze this equation from that, you will get your factor of safety. So that's how you can design the spring. Okay, so then you have a formula. See, you have a problem on this. See, in that clearly you can see that anyway we'll discuss this problem in the next class. But what I want to stress here is, if you look at the last line of the problem, determine the factor of safety used in the design on the basis of fluctuating stresses. So that means, if in the question, if he has given, or if I use the sentences fluctuating stresses, then only use these equations. Otherwise, use only static load equations earlier. So if he has not mentioned anything about fluctuating stress in the problem, if this word is not there in the problem, don't go for the design against fluctuating load. Even though the load is varying from, let us say in the problem 2, we see load is varying 300 to 150. Even though the load is changing, still we'll use the static design procedure for the static loading only, not for the fluctuating load. If this word comes in the problem, fluctuating stresses is there, then you have to use the static load equations or fluctuating load equations. Anyway, we'll discuss this problem in the next class. So I'm closing the class now today. For the today, okay. So it is over. Next class we'll discuss this problem. If you have any doubt now in today's discussion, then you can ask. So otherwise, upload your attendance in the classroom and then you can also leave the class.